All right, and we have Josephine Wong next up.
Yeah. So in my talk, I'm going to be transitioning a little bit away from cosmology and focusing more on the high energy universe. So my talk's on using X-ray polarimetry to study pulsar wind nebula, or PWN. So the general picture of how pulsar wind nebula works is that there's a central young energetic pulsar, and it's surrounded by a wind of relativistic charged particles. And you can kind of see a diagram of that over there. And the way this charged wind comes about is because the pulsar has a very powerful magnetic field on the order of 10 to 12 Gauss. And it's also spinning very rapidly with periods between tens and hundreds of milliseconds. And it's also made up of highly conductive material on the interior, typically made up of electrons and atomic nuclei. And when you have a combination of all these things, what you end up is something that happens in a Faraday disk, where because of the spinning charges in the magnetic field, you create an electric field that is able to pull charges off of the surface of the neutron star into the surrounding medium. And those charged particles are then loaded onto the magnetic field lines, and they can get accelerated on these field lines and escape, forming a wind around the star. So here's a animation of basically that happening. So at the highest order, we can treat the neutron star as a magnetic dipole. Some of the field lines are closed, and others are forced to be open because they cross a boundary called the light cylinder radius, which is the radius at which, if you're co-rotating with the star, you're going to be moving at the velocity of light. And so particles that are loaded onto these open field lines, they can't possibly move faster than the speed of light, and so they are loaded onto these open field lines and allowed to escape. And it's these escaping particles that form this wind nebula. And also, I'm wondering if I can play it again, but in the animation, you can see that there are also areas where you see pulsed emission. And those are coming from particles that are accelerated. So that's indicated by the pink regions. So that pulse emission comes from particles that are accelerated within the light cylinder radius. Right. All right. So some typical characteristics of PWN and what they're generally like. So the most iconic, I guess, archetypical picture of a PWN is the crab, where you have a toroidal wind around the pulsar, and also commonly jet-like structures. But you can also have very different looking PWN. So for example, this is MSH 1552, also nicknamed the cosmic cand. And you can kind of see why we've named it that, because there are these filamentary structures that extend all the way out as far as 6 arc minutes from the pulsar, forming these finger and thumb-like structures. But you can also have very different looking PWN that we've named the mouse. Vela is also one of the brightest PWN objects. Test 75, the duck, puppy, turtle, kookaburra. So you can kind of see a trend here in how we name our PWN objects. So some of the general morphological and energetic properties of these objects, the wind is highly relativistic, reaching gamma factors around 10 to 6, with a flat redox spectrum and X-ray photon index that's relatively hard, around 1.3, 2.3. They have very well-organized magnetic fields with a high degree of linear polarization. And if you look at these objects in X-rays, they're smaller because of the synchrotron burnoff of higher energy electrons. And as I mentioned, the toroidal wind and jet structures. And these are some of the most famous or brightest of these objects. So now I mentioned that, earlier I mentioned that we can study these objects, or these objects have very high linear polarization, which means that polarization can be a useful tool to study them. So the reason why they have such high linear polarization is because of a process called synchrotron radiation. And this comes about because you have these charged particles that are moving, that are accelerated in the magnetic field, and they radiate in a very ordered direction because the magnetic field lines themselves are very ordered. And for the photon indices of these objects, we can expect linear polarization up to 60 and 70%. So I've kind of mentioned that using radio, we kind of see, or with X-rays, we see a different, smaller, we get a smaller image of the PWN. And that's because we're looking towards the innermost parts of these objects. With radio, we look farther out towards the tails of the wind nebula. And because synchrotron radiation is multi-wavelength, which means that we can study, it spans from radio up to all the way up to gamma ray energies. We can study polarization at multiple wavelengths and kind of probe different synchrotron regions in the PWN. Radio polarization is something that we've been doing ever since we discovered pulsars in the 1960s. And the reason is because it's not too hard to make a radio polarimeter. We just either use a dipole antenna or attach a polarizing filter at the end of a antenna dish. But X-ray polarimetry is much harder because in X-ray astronomy, we typically work in counts rather than energy. And so we have to basically, in order to find or measure X-ray polarization, we need to measure the polarization of each photon that comes into our detector. But we have made some progress. So in the 1960s and 70s, we made basically our first X-ray polarization measurement of the Crab Nebula, detecting around 20% linear polarization, which confirms the synchrotron origin of the X-rays. But now, in December of 2021, we launched XP, which is NASA's first X-ray polarimetry mission with imaging capabilities. And that makes it very useful for studying extended objects like PWN. And so far in the past 1.5 years of XP observations, we've studied a whole class of different objects. But in this talk, I'm going to be focusing on pulsar wind nebula. So I'm just going to be talking about two sources. First is the Crab. So here is like an animation. We've stacked like 7 pictures that we've taken with Chandra between 2000 and 2001, and you can kind of see like the outflow in the jets, and as well as the expansion of the radio outflow of the wind. So basically, what did we measure? We saw that the magnetic field lines, which are perpendicular to the polarization direction, follow a toroidal pattern. There are low levels of polarization at the edge of the torus, and that's mainly because of the polarization angle changes very rapidly at both sides, and so we get a depolarizing effect. Meanwhile, the north and south regions have are very highly polarized at up to 50% polarization. Meanwhile, the pulse emission itself is only polarized up to 15%, and we also find statistically significant differences from the optical measurements. And so some of the things that this tells us is that the Crab has a toroidal magnetic field where synchrotron processes occur, which is kind of what we expected. But things that we didn't quite expect is that the polarization patterns in the nebula are much more patchier than we thought. And this may be possibly due to variations in the local magnetic turbulence, because the patchy distribution does not correlate with the X-ray intensity. And also, the levels of the polarization degree itself is also different from what we expect based on current simulations. So this is telling us that there's something, some physics that we're not quite capturing currently in our understanding of the radiation processes in these pulsar wind nebula. And then the second one that I'm going to talk about is Vela. So this is a polarization map of the Vela Nebula, and integrated spatially, so across this entire region and with energy, we find polarization degrees up to 45% with a angle that's aligned with the symmetry axis. We, based on the energy spectrum of this object, we expect synchrotron. We expect linear polarization up to 66 to 72%. And we do see that certain regions reach within 1 sigma of this limit. So this region here, as well as certain areas of the nebula that we decided to analyze. And so this is telling us that the Vela has a very highly uniform toroidal magnetic field structure. And so in that map there, the white lines are radial polarization vectors and the black lines are the X-ray polarization vectors. So by comparing those two, we see that the X-ray emission is surrounded by older, cooler electron population that is also pretty highly polarized, which means that the magnetic fields are minimally turbulent, extending all the way out to this radio emitting region. Also based on the energy spectrum, we don't believe that this other way of creating high energy photons called diffusive shock acceleration is not the accelerating mechanism, and it's most likely synchrotron. Magnetic reconnection or synchrotron processes. So here's a summary of my talk, and also as in terms of future work. So we've also observed 2 other objects, MSH and BO540, and the papers on that are coming out soon. We're also getting more observing time on the crab, and they'll add statistics to our current data set, and we might have new PWN observations next year.
Questions for Josephine? We have one here.
Do you expect the position angle to change in other wavelengths other than the X-ray? And how fast was that variation? You had a bullet point there, but you didn't elaborate.
So which one is this on?
You said PA, rapidly changing PA region in the plot.
Oh,
not
yes,
in the bullet point.
Yeah. So the rapidly changing polarization angle, we think that it's changing because it's following the toroidal pattern, toroidal structure of the wind. I'm not sure about radio measurements of this object, so I'm not exactly sure if the polarization angle might be different at radio energies. But I would expect that if synchrotron radiation is the reason that we're seeing this polarization, and I would expect that it would be a similar polarization angle.
And rapid, by rapid, you mean seconds or days or years?
Yeah, so I guess by the rates is with spatially. So it's rapidly changing with spatially, yeah, as opposed to time.
Back here.
Thanks for the great talk, Josephine. I'm curious if you could say a little bit more about the differences between the radio polarization and the X-ray polarization that you saw in the Vela pulsar.
Yeah. So what we're seeing here is that, so the white lines are the radio polarization vectors, and they do not overlap with the X-ray region. So that's telling us that the more powerful, I guess, the higher energy, processes, I guess, are happening within the inner parts of the nebula, and that's where we see the X-ray like emission mostly, and then farther out, that's where we see the lower energy polarization, because yeah, I think it's just that like the farther out you go, the photons lose energy, and so we don't see them in X-rays, but in radio instead. But they still follow like the general like toroidal structure, because these lines generally follow the magnetic field.
Firstly, let me, very nice talk, but underscore what a brilliant success XP is being, and
Yeah.
it's fabulous. The question is, if you just look at that, there are jets, there are magnetic field lines wrapped around it. Let me ask the leading question. Do you think that might possibly have a message for some other jets we may see elsewhere in the universe?
A message for other jets.
How they are made.
Oh, I guess these jets are coming from like outflows that are along the magnetic field axis, and so maybe we would expect something similar for other objects.
Okay, all right.
Sorry.
This is super cool stuff. I had a quick question just to get a sense of scale. When you talk about looking at the pulsar wind nebula, for example, the crab, is that the size of the full supernova remnant? Is it just like the central part? Is the rest of the supernova remnant polarized also?
Yeah, so it really varies depending on what object you're looking at. I think for the crab, since it's much younger, it's like about 1,000 years old. It's still contained within the supernova remnant. But if you look at some of these other objects, which I put up here, you can see that some of them are, like, for example, the turtle. You can see the supernova remnant shell around the central PWN. And in some cases, the pulse, like for example, in this duck PWN, you can kind of see that the pulsar has actually kind of crossed, like penetrated the boundary of the PWN and has moved out. So it kind of depends on, how old the system is. But yeah, it really varies. And like the size of the nebula also kind of varies. So for example, the crab PWN, it's about 10 arc seconds across. But for MSH, we're looking at distances up to like arc minutes, like several arc minutes.
Fantastic. Thank Josephine again.